This is Chapter 6, Lesson 2, Mechanical Waves. In our last lesson, we did the Slinky Lab. We saw transverse waves that wiggled sideways and went down the slinky length. We saw longitudinal waves that compressed and expanded the slinky links. We calculated the speed of many waves and had different amplitudes, and we calculated the speeds of waves in different kinds of springs under different conditions. So to warm up, let's remember, last lesson, we read about water and earthquake waves. We saw in number 2 that a wave's speed does not depend upon how big the wave is. Whether it be a little wave or a big wave, it still travels through a medium at the same speed. Number 3, does a wave's speed depend upon the spring that it is in? Yes, it does. The more rigid the spring or the medium, the faster the wave is going to be traveling. Today's purpose. Today I will learn different aspects of sound waves, water waves, and earthquake waves. These aspects include size, speed, and energy. Relevance. This information will help explain why different instruments have their own unique sound. A common mistake in making movies will also be discussed. You'll be successful when I can use terminology correctly to describe waves, and when I can make predictions about the notes made by different instruments. First of all, the basics of sound. Acoustics is the study of sound. There are acoustical engineers. They design buildings to have certain sound properties, which is mostly in things like theaters, movie theaters, concert halls, and that kind of a thing, lecture halls. Number 2, define sound. We're going to say that sound is a repeating pattern of vibrating matter. The pattern might be extremely short, such as a clapping hand, or much longer, like the long note of a trumpet or something like that. Number 3, the medium is the material that the sound is in. And the atoms of the material are going to vibrate, and the electrical forces around one atom are going to push on the electrical forces of the other. Remember that every atom is made by a cloud of electrons, and those are all negatives. So when one atom gets close to another atom, the negative electrons push on the negative electrons of the other atom. They never actually touch, but as they get closer and closer, the forces build up, and eventually the atoms will push apart from each other. And this happens an awful lot like magnets. And so I have here a model next to my fish. Here's my fish, although there's Mr. Fish, there he is. Anyway, up here on the top I have a model of a medium. It's a set of pendulums, and suspended at the bottom of each pendulum is a magnet. And as one magnet gets close to the other magnet, it's going to push apart and cause the next magnet to move, which makes the next magnet move, which makes the next magnet move, and so on and so on. But this is an awful lot like how air molecules act in sound waves. So I'm going to hit the first magnet, and you'll see the wave-like pattern of vibrations go down these series of pendulums. And then it bounces back. So that is a model of air making sound waves. Next, let me get this to be refocused. Okay, that's close to being focused. We just did medium. Let's look at number 4. It's still not quite focused. Okay. Let's hope that works for you. Number 4, what is wrong with movies that show spaceships zooming through space? Well, there's no medium to carry sound waves. There's no air molecules up there to vibrate and hit each other in a repeating pattern. And so there is no sound in space. There are a few movies that get it right. Recently, there was a movie called Gravity and another one called Interstellar, and I believe that they do the space scenes very, very silently, and that's correct. But the Star Wars and Star Trek movies and those kinds of things with zooming spaceships is completely wrong. Okay, next, number 5. How is sound made? Sound is made by two different ways. Either vibrating matter pushing on the air, causing air to vibrate, or somehow you just get the air to vibrate by itself. So the vibrating matter pushing on air, that'd be like plucking on a guitar string. As the string moves back and forth, it hits the air molecules, causing them to move back and forth, and they pass it on one air molecule to another. The other kind of making sound, the vibrating air here, that'd be like playing a flute, where you're just blowing air across an opening, and the air, as it moves around the opening, starts the vibrations. There is a little toy here that I have called a sound tube that makes sounds as you whirl it around. And let me play a video that has a demonstration of that.
So this is very cool. Look at this. This is what they call a sound hose. And it's just a piece of tubing, so you can see it's a long piece of tubing. Open it both ends, right? Right, now here's the amazing thing. Watch this. They just give it a little whirl. Oh, no, you can do this. You can do a little blow inside. Ooh, that's pretty fun, huh?
Ooh, if we had a lot of wind, we would have a bigger sound.
Well, we could do this for 2.5 minutes. But we're not. You hang on here like this, and if you get a little swirl, so watch this. If you swirl, listen to that. Is that nice? Okay, now keep it going like that. I'm going to go a little, oh, listen to you a little faster. Watch this. Oh, that's pretty good. Now faster on that one. Ready? Oh, here we go. Faster on this one. Go faster. Come on. Come on. Okay. So,
That's, you have mini octaves on yours. Yours is much better.
Musical fifths, if I'm correct.
Is that what that is?
Absolutely. Those people in the audience. All right. So the reason that this works is very, very cool. Because if you know something about this, you will never look at your vacuum cleaner hose the same way again. So here's what we're doing. As you swing this around, you're actually causing air to come in here. And because this is rippled on the inside, so put your finger inside and kind of feel. See, there's ripples that are here on the inside.
Ridges.
So those little ridges. So here's what happens. The molecules come in here, hit the little ridge, tumble, and fall, and they create these little vortices. I know, it's pretty high science.
Vortices.
Vortices.
Wow.
So next time you're at a cocktail party, you can say, well, I was just swinging around a tube, and I created a
capturing
vortice.
some molecules to roll
so,
them
so
over
if
the
you
vortices.
come through here like this, it actually is the air coming in. So if you stop it here like this and try to swing it around, it'll get you no sound at all. And watch this. This is a cool experiment. Paul Doherty is out at the Exploratorium in San Francisco, and here are grown men with PhDs doing this stuff. All right, so here's the bag. Right. So now watch what happens. We'll swing this around and watch what happens. Ready? So here we go. Nice sound, nice sound, nice sound.
A vacuum.
Look at this, look at this, look at this.
Go for it.
No more sound. Is that cool?
So it actually draws the molecules.
That's right. And so the air is actually coming through it. So if you were a manufacturer of like a vacuum cleaner hose company or whatever, you would never make the little ridges on the inside. Otherwise, every time you clean,
that's right,
what would happen.
Because they draw air in.
Now, Plumber pointed out to me that if you have a gas hookup outside, like for a fireplace or something, they never use this corrugated kind of pipe because your gas place will whistle.
Enough.
But then I got thinking, you know, this is a cool one, but today we took out our kid cam and learned that maybe you could find another one. So take a look at this on our kid cam here, a bigger whirly.
A bigger whirly.
Fortunately, this door had a big whirly, and I got a driver. All right, so you just take the tube and you put this in out the window and you catch the air, and you just have a really good driver. All right, so drive. Here we go. Problem is, the guy next to you thinks that you're gonna bazooka him. All right, here. Listen to that. Listen. Look at that. 25 miles an hour. 30 miles an hour. All I have is 2 words: road trip. This is awesome. It's science, people. See, and there it is. See, now this is the biggest whirly in the world. Isn't that awesome?
Right.
So I was going to whirl it for you today, but sticking outside the car was great. And I had a
Much
driver,
more
just in
fun.
case anybody was wondering.
Yes,
A little
right.
driver that was there. And,
Yes.
and I'm telling you, I'm going to hook this on with duct tape to the
Other
you didn't get to
motorists.
see that part.
Okay, enough about that. Back down to our notes. Number 6. Define region of compression. That is where the molecules are closer together than normal. And a region of rarefaction is where the molecules are more spread out than normal. Remember, with the slinky wave, we had 2 kinds of waves. A transverse, where we were shaking it side to side, and we also had something called longitudinal, where we momentarily squeezed the slinky and then stretched it out again. And we could see the places where the coils were closer together than normal, that area of compression, we could see that move down the slinky and back again. Same thing happens with sound waves. Number 7. When sound waves have this happen, we have areas where the molecules are far apart and areas where the molecules are very close together. Each molecule itself is only vibrating a little bit, but when the molecules all move in a pattern, they end up squeezing in one area here and then spreading out in an area there. The next moment, these guys are going to squeeze together and these ones are going to spread apart. So the region of compression moves down the line, even though each molecule only moves a tiny, tiny bit. Number 8. Sound waves are longitudinal waves all the time. However, it is hard to draw longitudinal waves as seen above. To simplify things, diagrams of sound waves are often shown as transverse waves. But remember, sound is never, ever, ever really a transverse wave. But it's easy to draw on a computer screen or other kind of instrument. So, in these such cases, what do the crests represent? They represent the areas of compression. Number 9. Normally, the areas of compression and rarefaction move as a pattern of motion moves from the sound source. However, in confined areas, the reflections of the wave can interact and make the wave look like it's frozen. And the result of that is something kind of interesting called a Rubens tube. And I have another video, this time of Mythbusters, showing a Rubens tube.
Adam and Jamie investigated the viability of fighting fires with sound waves. But what we didn't have time to show you was when they explored another fire phenomenon, the Rubens tube.
This is a stunning visual representation of a sound wave. Now let's fire it up and see what it does. All right.
It's a classic physics experiment that has recently become an internet phenomenon. A length of pipe is perforated along the top and sealed at both ends. One seal is attached to a small speaker, the other to a supply of a flammable gas. The pipe is filled with the gas, and the gas leaking from the perforations is lit.
Oh, it's beautiful. So this is called a Rubens tube, right?
Yep, it's Rubens tube, all right. And what you're seeing is a standing wave rendered in fire. This is how it works. When the guys play a tone through the speaker, the sound wave enters the tube, and the confined space creates reflections and interference, which combine to create a standing wave. The standing wave affects the air pressure inside the tube, which affects the amount of gas coming out of each perforation, which affects the size of each individual flame.
What we're looking at is areas of higher and lower compression being made by the sound waves down the tube, affecting how much gas comes out of each hole.
If you keep the frequency constant, you can determine the wavelength by simply measuring it with a ruler. And if you think it looks familiar, it probably is. Rubens tubes have been around since 1905, when Heinrich Rubin fired up the first.
Look at that. Yeah, we're watching the waves pile up. Yeah, totally.
It worked.
That is very, very, very cool.
Here's another video of somebody who made it in their garage and played some more modern music. That's kind of fun. Going back to our notes. Number 10. Define wavelength and give its variable and unit. Wavelength is the distance from one crest to another. The crest, remember, is the top of a transverse wave. You could also say that it's the distance from one trough to another. It's going to be the exact same distance. But we'll make our definition here as short as possible. The variable for it, when we see it in an equation, is this very unusual thing. It's a Greek letter called lambda. It's sort of like an upside down y. The unit that we measure this in, well, it's a distance, and so the metric unit for distances is meters. Number 11. Define frequency and give its variable. State its metric units. We're going to define frequency as the number of waves that pass by each second. The variable is going to be a small letter f, and the unit is 1 over seconds. Sometimes you see this as the number of waves per second, and that's okay, but it runs into a few little problems, so we won't write it down here like that. It's just how many things pass by per second. And the abbreviation for that is going to be the hertz, which is capital H, little z. So when we talk about the frequency of a radio station being 96.1 megahertz, that means that the radio signal has a frequency of 96.1 million hertz. 96 million complete wavelengths hit your antenna every second. Number 12. The equation that relates frequency and wavelength is V equals F lambda. So the V is the velocity of the wave, the F is the frequency of the wave, and the lambda is the wavelength. And we have to have the special units in order for everything to cancel out and combine correctly. The frequency has to be in the units of 1 over seconds, or in other words, hertz. And the wavelength, or lambda, has to be in the unit of meters. So if we had a wave that had a frequency of 30 hertz, 30 per second, and a wavelength of 2 meters, we can multiply those together and get 60 for our velocity. But notice how the m multiplied by 1 over s gives us a unit of meters per second, which is what we want for a unit of velocity. So things work out just fine. Please spend a moment reading the next 2 paragraphs that are notes about how this equation works. Number 13. We hear waves of low frequencies and low wavelengths as low pitches. The lowest pitch that the average human can hear is 20 hertz. That means that the air molecules vibrate back and forth 20 times per second. And the typical wavelength for this is going to be 17 meters. So that's approximately the length of the room from the front of the room to the back of the room. One area of compression would be in the front, the other area of compression would be in the back, and the area of rarefaction would be in the middle. Number 14. By the way, the highest frequency that the average person can hear is 20,000 hertz, and that has a wavelength of about 1 centimeter, I believe. Number 14. In string instruments, lower notes are made by thicker, longer, and looser strings. So think about a guitar. The lowest notes are made by the thickest strings, and to make the guitar in tune, and you need to make one note or one string a little bit lower, you loosen up the string by turning the little knobs. Think about a harp. The longer strings are the ones that are lower notes. Number 15. In percussion, lower notes are made by bigger, looser drums. So you can think of a kettle drum being really big and it being low, whereas a bongo drum is a smaller drum, has a higher pitch. And with the kettle drums, they can actually play different pitches on them by pressing on a pedal at the bottom and making the drum head tighter or looser. And even other drums, like a snare drum, can actually be tuned by making the drum head tighter or looser. Number 16. In wind instruments, lower notes are made by longer and wider pipes. So this is how something like a trumpet or a tuba makes different notes. By pressing the valves, you are forcing the air to travel through different lengths of pipes and therefore playing different notes. Number 17. Define amplitude. Amplitude is the distance from the rest position to a crest or a trough. In other words, how far does it vibrate, the air molecule vibrate from its rest position to an area of compression, or from its rest position to an area of rarefaction. If I draw the sound wave as a transverse wave, the amplitude is from the middle resting position up to the top of the crest, or it's from the middle position to the bottom of the trough. A lot of people draw the amplitude from the very bottom to the very top, and that's wrong. Don't do that. That's twice the amplitude. Number 18. Amplitude is related to the loudness of a sound wave. The more the air molecules vibrate back and forth, the farther they vibrate back and forth, the harder they're going to hit your eardrum, and the louder our brain perceives that. Please, once again, read that common mistake alert. If you want, you can play with the tin can telephone that I have. The way that that thing works is to pass the mechanical wave from one can to the other. You first of all have to have the two people holding the tin can with the string taut. It has to be kind of tight with a little bit of tension to it. As one person talks into one can, the other person has their ear to the other can. The person's voice causes the air molecules to hit the bottom of the can, making the bottom of the can vibrate back and forth. This makes the string vibrate back and forth, pulling and tugging on the second can. When the string hits the other can or is tied to the other can, it makes the bottom of the second can vibrate back and forth, which causes sound waves to then travel to your ear. Number 25. Think about your learning. Please put a check mark by the stuff in the notes that you already knew. And then put a question mark by the stuff that still seems a little bit confusing, and you may want me to talk about it a little bit when I return to class. In our next lesson, we will apply and extend what we learned today to discuss how our ears detect sound waves. So it's going to be a bit of a biology lesson. At this time, please turn and do the next homework assignment.